Now, this pipeline, I've said, is embedded in the execution model of Visit and ParaView. So we will have VTK, Qt, Python, OpenGL, MPI, all enclosed into the application, if you want. And if I look at an example of visualization which I have done this summer, here's a pipeline which was executed for a large mesh of 150 million cells. And what I want to point out in this slide is that the execution of this pipeline, you see here we have a reader, the source of the data, a distribution filter which exchanges ghost cells between the multiple partitions, a surface extraction, a smoother, a normal, and finally the image. Well, the image, which is the last part of the pipeline here, takes about just a few % of the execution of the pipeline. Here I'm running on up to 96 parallel tasks because it's a very large data set. You see the reading part takes about 20, 30 seconds, and then all the rest of the execution of the pipeline here, which is not graphics related, takes the 95% of execution. So what is the moral of the story? Is that when we do large data visualization, we don't need a fancy set of graphics card, because the rendering is nothing. It's the very top part here is a few seconds maybe. But we need instead a lot of computing power and a lot of memory. Okay? All of this pipeline here, so if you want from the top of the pipeline up to here, this is only computation. No graphics, no interactive graphics where you move your model in 3D on the screen. So for this, I need a large cluster of compute nodes. And then finally, the rendering can be done on a desktop with a desktop quality graphics card. So Eiger, as you can see already today, is showing some signs of being old and tired. And Eiger will be replaced this year. I have sent out my list of requirements for Eiger. And what have I asked for Eiger to replace the cluster? I've asked here at the bottom for NVIDIA cards of the type Titan, so they're consumer quality, they're upscale, but they're still consumer quality graphics card. And for all the process, was conceived many years ago, I mean in computer terms. So that's many years ago means 6 or 7 years ago, something like this. They decided on a particular HJ5 storage, which is as close as possible to the internal memory organization of the data in the simulation code. So that works very well. It works for very effective and fast I/O from the simulation side. Then we go to visualization. I have a different architecture in terms of data objects in memory because I have the VTK pipeline in memory. The VTK pipeline has its own VTK object. The storage layout in memory of an unstructured grid is done in a completely different manner than it is done on the simulation side. So I cannot do, this is exactly the explanation, I cannot do fast, large block reading of data from the HDF5, from the existing storage into the visualization objects because they don't fit. I have to reorganize data in memory before I can place it into the visualization pipeline. So in fact, in this case, this reader here is something I have built, and this is typical of one of the services that I can do for your group, for your simulation. I can do custom I/O solutions for the visualization softwares. Because the point is, these scientists, some years ago, yeah, when the software was conceived, they thought about a storage solution in HJ5, but they did not think about the complete path all the way to actually reading back this data and using it. So there, we have to pay a large penalty of reading. This is the reader part. The second part that takes a lot of time is the distribute part here. This is a ghost exchange. This is another fundamental problem of data storage and parallel simulation. Usually, so ghost cells, do you all understand what I mean by ghost cells? There are different names for it. When you do a stencil computation, at the boundaries between two processors, you need to exchange data. Those data that you exchange, they're usually 1 or 2 grid lines, for example. You actually have to pass them from one processor to the other. They're called ghosts in the terminology of ParaView. They're called ghost cells or ghost nodes. This exchange I have to do because we don't actually usually store those ghost cells into the disk files. There's a good reason for it. When you run a simulation, one day you're going to run with 512 processors. Fine, you have a certain data distribution. The next day you have 2048 cores. So you need to reload your data, but the ghost cells are wrong now. So usually ghost cells are not stored. They are recomputed at the time you reload an intermediate time step to continue your simulation. So the same I have to do here for the visualization. And this is exactly a good illustration for this particular case here. There are cases where in parallel, the filters actually have to communicate between each other. So the way we do parallel visualization is by doing data parallelism as opposed to task parallelism or as opposed to time parallelization. In Visit and ParaView, we do data parallelization, which means we take a large partition, a large set of data elements, and when we divide them among multiple partitions, and then the same pipeline is replicated multiple times for as many MPI tasks as you have. It's duplicated blindly, except that some filters actually have to communicate to be able to do their processing. When you do parallel visualization, there are 3 different types of rendering which you can do. This is the first case where all those parallel pipelines work at the same time on their local partition of the data. And at the very end, we accumulate all the graphical objects together, and when we send them to the client. Okay, this is why I say it's a heavy rendering, because all of a sudden we have a parallel cluster here and we have our desktop here. All of a sudden the desktop has to do the rendering of the contribution of all the parallel servers. This can be a very large object. In fact, the example of this bone simulation, the object is 120,000 polygonal elements. So it becomes kind of heavy. The second option is to have every parallel pipeline do its own rendering using its local data. And then there's a final phase to create a final image called, using sort last rendering, called a composition phase. And this is how it works. Imagine here a 3D grid. Here it is. I'm computing an isosurface. So this is processor 0, I guess. Doesn't matter. It does 1/4 of the data, so it does its own isosurface. This is another processor, yet another one. Here we collect together all the images and we send them to the client. What does that mean? We don't send polygonal objects, we only send pixels to the client. So this is very fast. There. The client here would receive exactly a frame buffer copy of what was generated in parallel. And this is how it works. Imagine here I have, I guess 4, yeah. I have a space shuttle, flying object, divided amongst 4 processors. Each one does its own image, and then we combine them together 2 by 2. So here's how we do it. One more time, and then we have the full image. Okay? So the depth of this tree is exactly log n of the number of processing elements you have. Here we are only exchanging pixels. How do we do it here? Take any pixel on the image. You look at the depth information, the depth of each of those pixels on each processor, and you keep the pixel that is closer to you. It's all programmed for you. You don't have to do this. And this is the final image which you get at the end of this composition phase. You should ask yourself the question, is the ordering of composition independent? Or, I mean, does it matter? Here I have an animation of this done in astrophysics, and you can see that the final image actually looks correct from a set of local processor frame buffers which looked completely arbitrary. See here, we cannot make much sense out of this. This is due to the load balancing of the parallel job, but at the very end we compose those images together and they look correct. So the answer to the question, is it order independent? Yes, it is. So now you are free to go and do your visualization in parallel. You don't have to worry about the ordering and the distribution of the data among your visualization pipelines. The final set, the final option is to do tile display, but I don't have one here anymore. A tile display is more complicated because you have a different number here of displays as you have a number of partitions. So it requires more computing again. So there's the summary. The pipeline we've seen here. This pipeline is a bidirectional exchange of data. It's very important to have information about the metadata so that we can plan the distribution of data among multiple tasks ahead of time. And then this subdivision is based on something called the extent translator. Here's another example in 2D this time. This is a map of Europe. It's an old image, actually. The coloring doesn't look good, but this would be the type of distribution the software would do for you automatically. This is a quad tree subdivision. You can see processor 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc., all the way to 15. This is because I said I want to run with 16 processors. If tomorrow you give me 256 processors, I will do a different quad tree. Of course, the pieces would be smaller, but the visualization result would be the same. This is what motivates the discussion of having a two-pass visualization pipeline where we exchange first the dimensions of the grid, then the software looks at how many processors are available, and then it does the math to say, I have 256 processors, I have a mesh which is, I don't know, 4096 square, I divide that into a binary tree. The examples of 5 minutes ago with the unstructured grid of the bone model pipeline here takes about just a few % of the execution of the pipeline. Here I'm running on up to 96 parallel tasks because it's a very large data set. You see the reading part takes about 20, 30 seconds, and then all the rest of the execution of the pipeline here, which is not graphics related, takes the 95% of execution. So what is the moral of the story? Is that when we do large data visualization, we don't need a fancy set of graphics card, because the rendering is nothing. It's the very top part here is a few seconds maybe. But we need instead a lot of computing power and a lot of memory. Okay? All of this pipeline here, so if you want from the top of the pipeline up to here, this is only computation. No graphics, no interactive graphics where you move your model in 3D on the screen. So for this, I need a large cluster of compute nodes. And then finally, now this pipeline, I've said, is embedded in the execution model of Visit and ParaView. So we will have VTK, Qt, Python, OpenGL, MPI, all enclosed into the application, if you want. And if I look at an example of visualization which I have done this summer, here's a pipeline which was executed for a large mesh of 150 million cells. And what I want to point out in this slide is that the execution of this pipeline, you see here we have a reader, the source of the data, a distribution filter which exchanges ghost cells between the multiple partitions, a surface extraction, a smoother, a normal, and finally the image. Well, the image, which is the last part of the